I just have a short presentation of what I've been telling you earlier, but with some of the pictures easily demonstratable or on the screen through the PowerPoint presentation. This is called Introduction to Soil Mechanics or / Geotechnical Engineering, as I mentioned to you. And basic concept I think I mentioned to you. Here is a structure. It's a multi-storied building. Let's say it's a simple residential one. It has to rest on the ground. And unless you make sure that we are able to transfer the load from here to the ground, we will not be successful in constructing this building and delivering it to the people. So that is basically the whole idea. But if you look at the changing pictures here, you will see several applications. This is a waterfront structure that you can see. This is a reinforced slope. It's an industrial one. This is a canal, and several structures that we as civil engineers build in order to provide facilities to society. In a typical geotechnical project, if you look at it, if you go to any site, this is the construction site, people will have to excavate, then construct something. So what we normally do is pick up some samples from here, take them to the laboratory. It's called geotechnical laboratory, or you can say for geotesting, and from there we determine the properties. As I mentioned to you earlier, the material is not manufactured, so I need to pick it up from here. I can also drive something and try to get the resistance and determine what is happening or what is the strength of the ground there. Once you find out the properties in the laboratory, we pass them on to the design office for design and analysis. So once you give the properties, a structural engineer, a geotechnical engineer will give you the design for the structure. And once the design is given, we come back to the site and we construct the structure. So please remember, it starts with the site, goes to the laboratory, does certain amount of analysis, and comes back for construction at the site. Unlike concrete and steel structures, we need to also specify the method of construction in many cases. We'll talk of that a little later, but I want to give you the kind of application that we mentioned earlier where you need geotechniques very much. Look at this small building or a medium-sized building, but the main thing is the ground here is reasonably good. For example, if you happen to be in Hyderabad, in most of the areas you get very strong, stiff ground, in which case we are able to just dig up maybe 1, 2, even multi-storied buildings. They are able to go to 3-4 meters. Unless they want a basement, they put the foundation here and construct it. What do you do? Transferring building loads to underlying ground for firm soil or light loads, in which case we go for shallow foundations. Shallow means I don't need to excavate too much into the ground on the order of 2, 3, 4, 5 meters because the soil here is strong and the loads are light. Now look at the other extreme. This is a way in which you can see how the shallow foundations are constructed. This is the actual footing and the reinforcement. This gets embedded into the columns, and that is how the structure is built. Then we go for the next extreme, what we call as deep foundations. I have a heavy structure, a multi-storied building. Nowadays you are having maybe 10, 20, 30-storied buildings, and you are not building in Hyderabad, but you are building, let's say, in Visakhapatnam, Krishnapatnam, Machilipatnam, or go to metros like Calcutta, Bombay, Chennai. What you find is a very soft, weak soil here. For example, in Cochin, this thickness of the soil is 60 meters. In Bombay, you will find around 20 to 30 meters. Visakhapatnam is around 15 to 20. Even Kakinada has the soft soil. Now, if you want to build a heavy structure, this soil cannot take it, which means you have to transfer the load from the structure to a hard stratum. If you get a bedrock, it's fine. If you don't get bedrock, you have to use appropriate stiff material. How do we transfer this load? Through these elements which are called piles. A pile is nothing but like a column. I can have a column above the ground, but if I construct the same column inside, it's called as a pile. A column can be constructed above ground with formwork, but inside the ground I can't remove the soil. So what we do is we try to drive the piles or excavate a hole, fill it with concrete and reinforcement, and then I'll get the pile foundations. Then of course we do provide a raft or a pile cap here. On top of it we provide the building. So please remember, if the loads are heavy and the soil is weak, you need to go for deep foundations. And please remember, this soil has to be characterized as well also the soil at the bearing level. So you can see why geotechnical engineering soil mechanics are important. In a typical project, you can see how a large number of columns are cast, and on top of it, we'll cut it off somewhere here and then construct the cap and build the structure on top. Then we also need to support the soil. For example, you have a tunnel or a bridge or a viaduct. You must have seen while going around Hyderabad, for example, outer ring road has many openings. I have one road here, another road here. I construct a ROB or some kind of structure so that the vehicles can travel here. And similarly, a train or highway can go perpendicular down below. There is soil here on either side, and here the structure which is supporting the soil is called a retaining structure or a retaining wall. In the previous case, we had a structural load coming onto the soil. Here, the soil is transferring the load to the wall, and of course this wall again will transfer it to the soil below, but the two functions of a retaining wall is to retain the soil here. And this is a very important aspect of it for any underground passage, etc., or when you are looking at any of the flyovers approaches, we still have to have retaining walls on either side of the road. So what does it do? It prevents this soil from moving or spreading laterally. That's what we call as a retaining structure. You want to store water. How do we do that? In the good old days, for example, Nagarjuna Sagar, they were using masonry dam. But that being one of the largest, it took a long time. It's very expensive. What they have found is soil itself is a good one. And it's not something new for us. Even our ancestors, the first dam in India was built in the 3rd century in Tamil Nadu. And all they had done was use soil, two different types. So here, for example, I have a fine-grained soil, we call it clay, which will not allow any water to go. And then we provide a coarse-grained soil, we call shell, and then we can build it. Soil is the cheapest engineering material. For example, a cubic meter of soil may cost you only about 500 rupees, whereas a cubic meter of concrete will cost few thousands of rupees. A ton of steel nowadays is going around 50,000 to 60,000. And soil is something which is stable. Nothing will happen to soil even after 100 years, because soil has been there for millions of years. Whereas you cannot think of concrete being safe after 100 years. It's likely to deteriorate. Steel can get corroded. So you can see, if I want to build a dam, I need to build an earth dam here, which is the cheapest, easiest form. You will find several dams in Andhra Pradesh, including the latest Polavaram is going to be of this. And in our good old days, all the village tanks were built with soil only. Imagine 200 years ago, there was no cement, no concrete, but people built the tanks. And for example, even Hussain Sagar is made out of, except for the spillway, which of course is a masonry one. So you can see earth dams are good for impounding water. You can also have concrete dams, weirs. For example, Dhauleshwaram weir or barrage or Anicut is made out of masonry and concrete. Then we still have a problem. I have a concrete dam. I'm storing water. You want to store water, but are you sure the water will not flow through and come out on the downstream side? So I had to worry about the seepage below. And this is another aspect of geotechnical engineering. So I need to find out what is the hydraulic properties here and what is the flow phenomenon, which I said is seepage. That is something that you need to worry about and analyze. So another application, even if you have concrete dam, masonry dam, you need to. One of the most classic examples of dams is the Three Gorges Dam in China. It's the largest engineering project in the world for all time, and it has costed more than few billions of dollars. It was completed about 4 or 5 years ago, and interestingly, we also use dams, for example, like Sri Salem, to generate power. Sri Salem Dam generates few thousand megawatts. This Three Gorges generates 22,000 megawatts of power, and they're going to enhance it to something like 30,000 megawatts. You can see that this whole thing is a civil engineering wonder. But for this, the economy of China would have been greatly affected. Now, how could you build this without looking into the strength of the ground, the hydraulic properties, the stability of slopes, etc.? Anything you want to do here would have been a very relevant for geotechnical engineering. Here is a spillway in one of these concrete dams. Again, this spillway has to rest on the ground, which means you need to study the characteristics of the ground. We do a lot of earthworks. Suppose I want to build, if you have seen, for example, the 4-laning of road from Hyderabad to Vijayawada, or all this national grid that we have, golden quadrilateral, etc., you have to first excavate, recompact it, so that the road is very stable and safe, and you can drive at something like 80 to 90 kilometers per hour. So there's road work you can see here, needs removal of material and recompacting so that you get a very strong, stable base and sub-base, etc. So I call it sometimes as grading, and here is called preparing the ground for before construction. So you can say this is the beginning of a heavy project. Then of course we are going to provide different layers here, and you need to make sure of separate specific materials called geosynthetics nowadays we are using in the ground. We cannot use reinforcement in the form of steel because steel gets corroded. Fortunately, we have a synthetic material called geosynthetics, and we are using them in the roads to make their life longer. If you go around any city, any flyover now, you cannot help noticing these reinforced earth walls. In the good old days, we are using, right from the beginning of this Christian era, people were building with stone, then later with concrete or masonry, etc., and steel also. We found that recently, in the last 30 years, you can use the geosynthetic reinforcement and build what is called as a reinforced earth or soil wall. These are much more easier to construct, cheaper by about 10 to 20%. So when I want to construct it, I'm going to use soil here, a good granular material, and I'm going to use some geosynthetic reinforcement. So you can see, if I want to build a reinforced earth wall, again I need to know the properties of the material that I'm going to use. And the amount of reinforcement I use is a very, very small fraction. So this whole wall will consist of soil alone and very little manufactured material. What you see as concrete is nothing but a fascia. It's a protection, nice to look at, etc., but no structural component. If you have a steep slope and you want to stabilize, instead of providing reinforcement and constructing, what we try to do is we drive nails. Like you drive a nail into the wall, we use the stabilize the slope with this kind of nailing. So when I'm trying to protect this slope, I'm going to again use some kind of nailing. And here again, how do I make sure what is the proper design? Without knowing the properties of the soil, we cannot design this nailing. What should be the length? What should be the spacing? How do I construct it? They all depend on the soil properties. Many of the projects near the water, how do I construct a berth here? Here is a seawater and a harbor, and I want a ship to come there. I need to provide a platform so that whatever crane is here, it can unload, or if you are a passenger vehicle, they can go and get into this. So temporarily or permanently, we use what is called as a sheet pile. Now this is a very long, maybe something like 15, 20, 30 meter long steel material, you need to anchor it sometimes, and again we like to check the stability of this, design it properly by using principles of geotechnics. Again, I need to know the shear strength of the soil here, what is the compressibility, etc. In the good old days, they were using timber, but we don't use it now because the size and projects are very high. If you had looked about 200 years ago along the Ganges, they had these timber-driven piles, but now we are using interlocking steel. We are also using sheet piles for very many structures. In one of the recent probably metro construction in Hyderabad, you may find these to support the excavation that they had to make in order to found the pier at a depth of 6 meters or 7 meters. Wherever you also have, for example, in Chennai, you have high groundwater table. I want to provide a raft. So in order to do that, first I drive the sheet piles, remove the water, then cast the concrete and bring the building. So this is what you call as temporary works. The sheet pile here is not there for long. It is only during construction, and once I finish the job, I remove them. In several of these power projects along the coast of Andhra Pradesh, they are using sheet piles as a temporary measure because the foundation has to be located at a depth of 4, 5, 6 meters, but the water table is very high. So I support the soil here with sheet piles, pump out the water, make the excavation dry, and then construct it. You want to build a bridge pier in the river, for example. How do you think in Godavari or Krishna? Now they are going to build another rail-cum road bridge on Godavari near Rajahmundry. Another bridge is coming on one of the branches of Godavari, and in the river you have to build an island. If I want to do that, again I can provide sheet piles all around, fill it with soil, make a platform, sink a well or whatever it is necessary, and build the structure. Those are called coffer dams. They are temporary structures again. They may be dismantled after use. I was mentioning to you that slopes may not be stable. Fortunately, we are in a very relatively flat area, except for some excavations. About 1 month ago, there was a landslide or a slip like this in Jubilee Hills because somebody made a vertical cut and he forgot that the soil here may not be strong. But usually along, for example, Ooty, Kodaikanal, Eastern Ghats, Western Ghats, Himalayas, etc., the slope instability is a very common problem. Because of the cutting or something we do, when we interfere with nature, the soil becomes very unstable. As you can see here, some of these slope failures occur. So one of the last sections that we are going to talk about will be slope stability. The reason being landslides are very, very common feature. Now, again here we don't have a major problem, but I have a major excavation to be done, and if I want to support these structures, I need to support by means of temporary support. For example, in Delhi Metro they had to do it, Calcutta Metro they do it enormously. This is again tunneling. For example, Delhi Metro had a series of tunnels. Or for the example, irrigation projects, the Jammu to Srinagar railway line had several tunnels. This is again a civil engineering activity. We need to take care of the soil or rock all around. Then you want to make an excavation, you have to do some blasting. You have to make sure when you do that, we don't endanger the adjacent buildings or structures. Then how do I make sure whatever we are putting back into the ground is safe and well done? So we have different types of what you call as rollers, and this is called a sheep's foot roller. When we look at compaction, we'll see that. This is the kind of normal roller that you know. This is the smooth wheel roller. You will see road roller there all the time, but this is for finishing. Whereas when I'm doing it at the base course level or subgrade level, I may have to have different ones. This is just showing you, it hasn't come to India, but very soon you probably in your professional life you will see this. The reason being, this is an impact one. It's not a circular wheel. When it is rotating, it will try to fall, and compact the soil. The railways are keen on using this because normally we use only 300 millimeters lift or the layer of loose soil. With this, I can provide half to 1 meter. The construction will be faster and the densification will be much better. So this is one of those methods. And if I can't do it by means of a simple roller, what we are using is what's called a heavy tamping. I take a heavy weight, drop it, and then compact the soil. As you can see, these craters, that is where the soil got compacted. This is one of the classic examples where NTPC built their big thermal project at Kodamkulam in Kerala on loose soil. They compacted by means of heavy tamping. This is another form of densification. One of the recent applications for civil engineers is a problem created by society. We have a lot of municipal solid waste, hazardous industrial waste, etc. Now you can't leave it because the leachate, once it goes into groundwater, you can't drink this water anymore. There are several places in and around Hyderabad or wherever there are industries where this has become a serious problem. So we as civil engineers and geotechnical engineers, we try to design the lining system so that the leachate, this is all the waste. Could be municipal solid waste, it could be chemical waste, hazardous one, whatever it is. Whatever escapes or comes from here doesn't get mixed with groundwater. Once it goes into groundwater, let me warn you, this water cannot be drinkable. And people may die even, and so we had to provide a proper geotechnical design for this. So as a geotechnical engineer, this could be one of the most challenging jobs. You also may have to worry about what are the gases which are being emanated from the waste and how do I collect it and use it or discharge it. We need several instruments now to monitor what's happening in the ground. So we have what's called as a cone penetration, then we measure the displacements, we can measure the loads, pressures, deformation, strains, etc. So we develop a series of equipment or instrument to do this. Whatever we do in the laboratory is not necessarily the best way. For example, if somebody is not well, he goes to a hospital and instead of taking samples and testing, they are using ultrasound, CAT scan, NMR, etc. Similarly, we try to test the soil or the ground in its own position. So I call it testing in the field. We also use a word called in situ, and we try to take samples to test in the lab, but we also try to test it right at the site. There are several such tests. One is called standard penetration test. In a very soft soil, we use what's called as a vein shear test. This is another cone penetration test. It's usually mounted on a truck, so it's very easy. You take it to the site, push the cone into the ground, and get the response. This is how we test in the laboratory. You have a soil sample, cover it with a rubber membrane, apply water pressure all around and vertical pressure. This is called a triaxial test in the laboratory. You have to do it very carefully to determine the strength and stress strain properties of the soil. We'll go discuss that later. These are the different types of testing in the ground. This is the most common standard penetration test. This is for soft soils. These are some more like our CAT scan and NMR, very powerful techniques from where I can get the properties of the ground very easily. And this is how a typical laboratory would be. People are trying to measure through a loading frame. Sometimes you use computer control, and we try to measure the properties. We need to have a certain factor of safety in order to make sure the structure is stable. Unlike structural ones where the factor of safety is more than 3, we use, because the soil, we have slightly less one. For earthworks, for retaining structures, they are less than 2. Whereas when it comes to foundations, of course, we go for somewhere between 2 to 3. Whereas I don't, even though it's a manufactured material, when it comes to steel, I use a factor of safety of 5 or 6. And here is the probability of failure. 1 in 500, 1 in 1500 for retaining structures, 1 in 5,000 for foundations. The reason being soils are much more adjustable, and even if there is some problem, they can take care of it. But there is no safety against bad design, poor construction. So whatever we do, we try to find out what is below the ground. We call it exploration. We do the foundations, we do the tunneling, etc. But one thing, let me tell you, if you do a good job, nobody will know. But if somebody does a bad job, if there is a structural failure, everybody knows. So a geotechnical engineer is called unsung hero. You do a good job, nobody will say anything. They won't even compliment. But if one does a bad job, then they'll say, you've done a bad job. Then if I look at the famous people who contributed, the earliest one who could, you can say, beginning of soil mechanics was Coulomb in UK, somewhere from 1736 to 1806. He came out with the shear strength of soil and theory for earth pressures. About 50, 60 years later, Rankine again in England has come out with theories of earth pressure and what are the states of limit equilibrium. We credit Terzaghi with the birth of soil mechanics. He wrote a book in German in 1925, and that is the time it's considered as the beginning of geotechnical engineering. His follower was Casagrande, then Skempton in UK, and these are some of the people. Norwegian, he is another famous professor in US at Purdue. Several of our Indians went and worked with him in Purdue, and then they contributed to geotechnical engineering. There are several such people in India too, but just some people. Just to give you an idea what a geotechnical engineer can do, here is the famous Tower of Pisa, which was tilting, and in 1991 it was stopped because it was so critical it may fall. Then three famous geotechnical engineers were consulted. They have suggested gradual removal of soil from one side, so the tower came back by half a degree, and it is considered safe, and for the last maybe 10 years it's open again, and they say this will not fail at all. This is one of the huge dams in USA, one of the tallest concrete dams, about 221 meters over dam. Look at this. And they had to design both the foundations and abutment to take care of the thrust from the water. You have seen so many tall structures. This is in our neighboring country, Malaysia, Petronas Tower. The foundations for this tower go up to something like 70 to 80 meters into rock. Burj Dubai has foundations going up to 90 meters. Such a tall structure you cannot design without proper foundation support. These are classic old ones, the pyramids, the Sydney Opera House. These are all the Greek and Italian and Roman structures. Thank you.